Hey everyone, and welcome to this brand new explainer. I am absolutely thrilled to have you here with us today because, man, we are going to look at a topic that is going to fundamentally shift your entire perspective on reality. We are going to completely shatter the illusion that you are sitting perfectly still right now. We're tackling a massive question today. How do the Earth and the stars actually move?
So let me ask you right off the bat. Are you sitting still? Or are you hurtling through space? I mean, right now, as you're watching this, you probably feel completely stationary, right? The chair beneath you feels solid, the room around you is totally static. But here's the thing, your frame of reference is entirely deceiving you. On a cosmic level, stillness is just an illusion. It's a trick played on you because everything around you is moving at the exact same time.
To really get a grip on this, we got to rewind all the way back to 1632 and look at a really famous thought experiment from Galileo Galilei. He wrote, "Shut yourself up below decks on some large ship. You'll not be able to discern whether the ship is moving." Basically, he realized that if a ship is gliding smoothly across the ocean, a person inside a closed cabin has absolutely no physical way to prove they're moving at all. This is the core concept of Galilean relativity. Motion is entirely dependent on your frame of reference. There is literally no ultimate absolute stillness in physics.
Section 1. The daily spin and orbit.
Okay, let's dive into this. To show you just how fast your personal ship is moving right now, we're going to embark on what I like to call the Great Zoom Out. We'll start locally with the movements we think we already have figured out. We all know a day is 24 hours, right? Well, sort of. A solar day is 24 hours. That's just how long it takes for the sun to return to its highest point in our sky. But a sidereal day, which measures Earth's rotation against the distant background stars, is actually 23 hours, 56 minutes, and 4 seconds. You might be wondering, why the difference? It's because we're orbiting the sun. Every single day, we move slightly further along our orbital path, which means the Earth actually has to spin about 1 extra degree every day just to point back at the sun.
But get this, Earth's rotation isn't just some perfect, unchanging clock. On June 29, 2022, the Earth's rotation was exactly 1.59 milliseconds under 24 hours. Our planet is actually speeding up. Why? Well, one super fascinating reason researchers point to is that polar ice is melting due to climate change. As that ice melts and the water redistributes toward the equator, the Earth becomes ever so slightly more spherical. It's exactly like an ice skater pulling their arms in during a spin. Thanks to the conservation of angular momentum, our whole planet spins just a tiny bit faster.
You know, it is just amazing to consider how incredibly long it took humanity to figure out we're even moving around the sun in the first place. Aristarchus actually proposed a heliocentric model way back in the 3rd century BC, but the idea didn't catch on until Copernicus published his model in 1543. Then Galileo had to vigorously defend it a century later. And it honestly wasn't until the 1730s that the French geodesic mission physically proved the Earth was bulging at the equator because of its spin. We have literally spent most of human history completely oblivious to our own cosmic commute.
And wow, what a commute it is. 29.78 kilometers per second. That is our orbital speed around the sun. To put that insane speed into perspective for a second, you are moving fast enough right now to cover the entire distance from the Earth to the Moon in just about 4 hours.
Section 2. Earth's long, slow wobble. So we're spinning and we're speeding around the sun, but as we zoom out slightly to the solar system scale, things start getting a little more complex. Our orbit is far from some perfectly smooth clockwork circle. We're traditionally taught that the planets orbit the sun, right? Technically, that's not exactly true. Because of gravity, the planets tug on the sun just as much as the sun tugs on the planets. They actually orbit something called the barycenter, which is the true center of mass of the solar system. Because Jupiter and Saturn are so incredibly massive, their gravitational pulls literally yank the barycenter around. This means the sun executes this complex little pirouette right in the center of the solar system, and Earth's orbit is constantly shifting and stretching to keep up with the dance.
And as we orbit, we also wobble. This is a phenomenon known as axial precession. Remember that equatorial bulge we talked about earlier? Earth is a bit wider around the middle. Well, the sun and moon tug unevenly on that extra mass, which creates a gravitational torque. Now, this doesn't pull the Earth over. Instead, it makes the Earth's axis slowly trace out this massive, cone-shaped wobble. It is exactly like a spinning top that's just starting to lose its momentum.
And that brings us to a truly massive cycle. It takes 25,772 years for the Earth to complete just one full wobble. The most mind-blowing consequence of this? Our current North Star, Polaris? Yeah, it's only holding a temporary title.
thousands of years from now, our North Pole is going to point to completely different stars. Our literal cosmic ceiling is fundamentally changing as we wobble.
Section 3. Dancing through the Milky Way.
Now, what's really interesting about this slide is how it addresses those viral internet animations you've probably seen. You know the ones, showing the solar system shooting through space like a vortex or a helix, leaving this cool trail behind. While visually awesome, they're actually highly misleading. They rely on what astrophysicists call reference frame chauvinism, basically suggesting that one perspective is the right one. In reality, our planetary plane, the ecliptic, is simply tilted forward by about 60 degrees as we travel through the galaxy. We're not being dragged in some crazy vortex, we are just tilted. To truly map our path, astronomers use a much better model called the local standard of rest. So, relative to that local standard of rest, our sun's path is definitely not a perfect circle. It's incredibly complex. Step 1, we're drifting inward toward the center of the galaxy at 8 kilometers per second. Step 2, we're drifting forward, moving slightly faster than a standard circular orbit at 5 kilometers per second. And step 3, we're currently moving upward out of the galactic disk at 7 kilometers per second. If you put all that together, our solar system actually moves in this really beautiful epicyclic flower pattern through the Milky Way.
That third step I just mentioned, our upward drift, causes something absolutely remarkable called the 60-million-year galactic bob. Because of the sheer gravitational pull of the galactic disk, our upward motion is eventually going to slow down. We'll fall back down, overshoot the middle, and pop right out the bottom. We complete this incredibly graceful vertical oscillation every 60 million years. And here's the crazy part. Some astronomers actually theorize that plunging through the denser central parts of the galactic disk might perturb asteroids and could be directly linked to mass extinctions on Earth, including the one that wiped out the dinosaurs 60 million years ago.
And this brilliantly illustrates how this complex motion creates very real, measurable phenomena right here on Earth. See, because Earth is orbiting the Sun while the Sun moves through the galaxy, our velocities actually add together. In June, Earth is moving in the exact same direction as the Sun's galactic path, so we hit our maximum galactic speed. But in December, we're moving opposite to the Sun, hitting our minimum. This works exactly like a car windshield in the rain. In June, because we're moving faster, scientists expect our planet to physically sweep up more dark matter particles. We literally use our changing galactic speed to help design detectors to find the invisible mass of the universe. How cool is that?
Section 4. The secret movement of stars.
But hey, we aren't the only ones moving. Let's shift our reference frame just one more time. When we look up at the night sky, it looks incredibly permanent, doesn't it? Well, it isn't. We have to understand a concept called proper motion. This is the measured angular speed of a celestial object as it moves across our sky. You see, the stars in our galactic neighborhood are not just painted onto some static ceiling. Every single star is orbiting the galactic center totally independently, each with its own specific speed and trajectory. Because our human lifespans are so incredibly short, we just don't notice it. But over millennia, the stars visibly drift. The familiar constellations we all know today are eventually going to stretch, bend, and completely change shape.
If you want real proof that the so-called fixed stars are anything but fixed, just consider Barnard's star. This is one of our absolute closest stellar neighbors, and it is zipping right across our line of sight at a transverse speed of 90 kilometers per second. It is moving so fast from our perspective that its position in the sky actually noticeably changes within a single human lifetime.
Let's move to Section 5 and see how this builds. Racing toward Andromeda.
Okay, we are going to execute our final great zoom out to the scale of the entire universe. First up, one full orbit of our sun around the Milky Way takes roughly 230 million years. The last time our planet was in this exact sector of the galaxy, the earliest dinosaurs were literally just starting to roam the supercontinent of Pangaea. But even our galaxy isn't sitting still. The Milky Way, along with Andromeda and our entire local group of galaxies, are mutually attracted by gravity and are plunging toward each other at hundreds of kilometers per second. Ultimately, physicists measure our absolute grandest motion against the cosmic microwave background, which is the lingering radiation from the Big Bang itself.
Which brings us to a final, pretty provocative question. If our planet is spinning, and our solar system is wobbling, and our sun is bobbing through a galaxy, and our entire galaxy is hurtling through the universe, what does it truly mean to be still? We circle right back to Galileo sitting in the belly of his ship. Stillness is entirely a matter of perspective. We are passengers on the most magnificent, complex, multi-layered joyride imaginable. I really hope this explainer has completely changed the way you feel the next time you try to just sit still. Keep learning, everyone, and keep wondering about this amazing universe.